Okay, so question 1 is if y is a differentiable function of t such that y is greater than 0 and dy dt equals ky for some constant k. K is called the proportionality constant. So
For two, it is also the same question, but in here, it is asking me whether we can use a separatable method to solve this differential equation. In order for us to solve this, we have to separate them into uh, into the similar terms into the same side. So in here, since we have dy and dt, we need to separate them. So we will use a separable method. We can put y and dy on the other side, and then k and dt on the other side, and then from that we can integrate it.
Question 3. The rate of change of y is proportional to y when t is equal to 0, y is equal to 2, and when t is equal to 2, y is equal to 4. What is the value of y when t is equal to 3? So in this example, we have exponential growth. Yeah.
okay, question number 4. The rate of change of y is proportional to y when t equals 0, y equals 0, and when t equals 2, y equals 2. So what is the value of y when t equals 3? I put 2.
Yeah, 2.
In 5, we're trying to find the k. So in here, I can use a formula y of t is equal to y naught times e power kt, and then we can plug in the numbers since our initial value is 2, and then I can also substitute the 2 comma 4 when t is equal to 2, y is equal to 4. From that, I would get 2 is equal to e power 2k, and then I put the natural log. So the e power will become ln e, and then it will be equal to 2k. On the other side, we will have ln 2. So from that, we want to find k. So we can find ln 2 over 2. If we want to be accurate, we can just leave it there like that. But since this is asking about decimal, I put it in the calculator, and then I get around like 0.3466. So I would round up to 0.35.
Question 6. The rate of change of y is proportional to y is basically the same question as the previous one. And it's asking about what y value is when t is equal to 3. And we've already know what k is from the last question. So we just plug it in, and we can get when t is equal to 3, y would be 2e to the 3 times k. And after we plug it in the calculator, we will get 5.656, I think. And if we round it to two decimal places, it's gonna be 5.66.
Question 7. If y is a differential function of t such that y is greater than 0 and dy dt equals ky for some constant k other than the separable method, we can solve these types of problems using linear method and integrating factor, and here I put true. We can set dy over dx equals ky, and then having dy over dx minus ky equals 0, so it's the same pattern.
For 8 is asking me this whether it's an example of exponential decay or not. So the question is asking about the number of the bacteria growing, and then in here I would say, like, for the exponential group, if k is equal k is like greater than 0, then that would be the exponential growth. But if k is negative and less than 0, that would be exponential decay. In here, when we calculate the k, it is greater, I get around like 0.4, so that is like greater than 0, and the rate is positive, so that would be an exponential growth. So the answer to this would be false, since it is asking if it is an exponential decay.
Question 9. It's the same question from the last question, and it's asking about the constant of proportionality, and we just plug p0, and e to the k is equal to 3 second p0, and we get e to the k is equal to 3 over 2, and we do ln on both sides, so we know k is equal to ln of 3 over 2, and after we plug this into the calculator, it's gonna be 0.4055, and we round it up to 0.41.
Like this.
Yeah.
Okay, so question 10. A culture initially has a p0 number of bacteria, t equals 1. When our number of bacteria is measured to be 3 over 2 p0, and if the rate of growth is proportional to the number of bacteria p of t present at time t, determine the time necessary for the number of bacteria to triple. So here we have first we set p0 times e to the power of k. Well, the function, we can set it to p of t equals p0 times e to the power of kt. So then we set that function p of t, which is p0 e to the power of kt, also to equal to 3 over 2 p0. So then we solve for e to the power of k. We take the natural log of in both sides, so we end up with k and ln 3 over 2. So then we need to find when p of t is equal to 3 p0. So we set p0 e to the power of kt equals 3 p0. So then we end up with e to the power of kt equals 3. We solve for t, so we need to take the natural log we end up with ln3 over ln3 over 2 because we have ln3 in the numerator, and in the denominator we have k, and k is equal to ln3 over 2. So rounding up, we end up with 2.71 hours, which is basically 3. So there we go.